So now that we have talked about electrical systems and mechanical systems, we need to talk about instrumentation and controls. Instrumentation and controls are the tools that we use to make those electrical and mechanical systems do what we want them to do. And here's an example of that. This is what's called a process control loop. So process control is just controlling some parameter, and we call those parameters processes. So it could be something that heats, something that cools. It could be level, it could be temperature, it could be pressure, it could be flow rate. All of those things are just a process. So in this control loop, and we'll see why it's called a loop here in a minute, we have feed flow coming into a tank. We have flow coming out of the tank into a pump. The pump is discharging into a level control valve, and the level control valve is going out to some other device. Now we want to maintain the level in this tank at a particular point. We call that the set point. So the level in this tank is going to be called our process variable. So level is our process variable that we're looking at. To measure that process variable, we have a level transmitter, and it just sends a signal back to the controller, and it compares the actual level in the tank with the set point. So you see the set point is coming in from some remote point above into the controller. It's being compared to the actual level measurement, and a controller output is being sent to the level control valve. So since the pump is discharging out through the level control valve, if the level in the tank is too low, it's going to close the valve, less fluid will leave the tank, and the tank's level would go up. If the level is too high, it would open the valve, and the flow rate would increase. The level in the tank would therefore come down. So all this system is trying to do is keep the level in the tank at the desired level, which is the level we're receiving from the set point. This is what all those parts and pieces might look like. So we would have some kind of a sensor, a transmitter that would send an electronic signal to the controller. The controller would send an electronic signal to the I to P converter. The I to P converter is current I to pressure P. So it would have an electronic input and it would have a pneumatic input, an air signal. So the air signal would come in, it would be controlled by the current signal. The air signal would then go to the actuator on the control valve. The control valve would open or close, and we would have achieved the desired outcome of either raising or lowering what's going on in the tank. So that process control loop that we saw in the schematic illustration actually manifests itself in these physical devices that we see in this slide. There are all sorts of control loops, but primarily we can lump them into closed loops and open loops. Most of the time we're going to have a closed loop system. Not always, but it's certainly the most common. In a closed loop system, we have a controller. In this case, we have a heating system, and the heating system is warming the room. When the room gets to be the right temperature, we reduce the amount of hot water flowing through the radiator. If the room gets too cold, we increase the amount of water flowing to the radiator. And since the radiator and the thermostat are in the same room, it's a closed loop. On the right, we have an open loop system. Here, we have a system that doesn't respond based on what's actually happening. It just looks at the outside air temperature, but there's no feedback. So it just gives you a flow of chilled water, providing some sort of cooling to a load, but it's acting independently of what's actually happening. since it's actually acting independently of what's actually happening, in most cases it's not as desirable as the closed loop where we have a feedback. A couple of names we just looked at: process control. That's the measurement uh, that is being used to look at whatever the process is. In other words, the physical thing we're measuring, and we're going to send that to the controller to make that adjustment. And variables are all of those different values that we talked about. They could be pressure, temperature, level, flow. We could have chemical measurements like pH, conductivity. There are as many process variables as you can imagine, but if you wanted to look at the most common ones, you could say temperature, pressure, level, and flow. So here are our variables. Um, most of any power system, any manufacturing system, can be designed to achieve its desired function by monitoring these 5 points. There may be lots of different levels and lots of different temperatures and lots of different flows, etc. But these 5 parameters, level, flow, pressure, temperature, and pH, are going to be the things we're going to monitor. And then we're going to have a set point, which is that desired level, the desired flow, the desired pressure, the desired temperature, or the desired pH, and have a control system that will help us maintain that set point. Another example of a control loop is a pressure tank that supplies um, water to a house, a variable frequency drive that's going to run a pump to control the pressure, a pressure transmitter that's going to try to measure the pressure in the line, and a controller that's going to take that pressure measurement and try to keep the pressure at the set point by increasing or decreasing the speed of the pump through the variable frequency drive. Here's another type of control. This is another level control, and this is a proportional controller. We talk about control as proportional, integral, or derivative. In this case, this is proportional control. So our proportional controller is set up so that we have a float, and when the float is up, the valve is fully closed, which means the tank is at its high level. When the float is all the way down, that means the valve is fully open and the tank is at its low level. So if you imagine that perfect is the float at midpoint, that's the desired level of the tank. The further away we get from the desired level or the set point, proportionally the valve is more or less open. So the further we are away from the set point, the more the valve is open or the more the valve is closed. In other words, the action of the valve is proportional to the error we have from the set point. We have all sorts of devices, and we can put these all together. I mentioned proportional. We also have integral control and derivative control. Don't get too freaked out by this little diagram. This is just showing you what we can do with these systems by having proportional, integral, and derivative control. We can control a very, very processed system with lots of different variables, and we can control it to a very exacting level using our control network. All sorts of devices here. We've talked about valves before. We had an example of a globe valve. We also had an example of a gate valve. We talked about quarter turn valves or ball valves. All of these different types of valves, three-way valves, four-way valves, we looked at all of those. We can connect those valves to a valve actuator. And a valve actuator is just a device that is going to use some kind of signal, some sort of remote signal, to operate those valves. And those valve actuators can be diaphragm operated, they can be air operated, they can be pneumatically operated with mechanical assists like springs, or they can be hydraulically operated. A lot of different types. So we're going to look at one here that's pretty pretty typical. And in this particular system, what we have is an example of a university campus. This is the University of Iowa. And in this particular example, we have a lot of process control going on because we have power distribution to the campus, we have water distribution to the campus, we have water distribution to boilers to produce steam, to heat and cool. We have gas that has to be provided to the natural gas boilers. We have solid fuel that has to be provided to the solid fuel boilers. And solid fuel boilers is just a nicer way of saying these things burn coal. But coal is a perfectly good fuel, and it's still one of the most common fuels we use in the United States. That steam then can drive steam turbines to produce electrical power. It can drive chillers to produce cold water. Well, if you think about trying to control all this, you have to have all those actuators to open and close all these valves that are moving all this fluid on the system. So we can use process control and instrumentation to monitor parameters, and then we can use the electrical and mechanical systems that we already talked about to achieve those outcomes. So that's kind of a little overview of how control systems interface with mechanical and electrical systems.